thank you, Laura, and thank you, BCS Society, for inviting me to give a talk or seminar on the cyber physical systems. As Laura said, my name is Paulius Stankaitis, and I'm a member of AMBER Research Group, which stands for Advanced Model-Based Engineering Group, and I'm part of Newcastle University. So maybe just a couple of words about myself. I know Alba mentioned, but since undergraduate degree, I've been in Newcastle, and I did my bachelor's and master's and PhD there, and continue working as postdoctoral researcher here as well. And most of my career, I worked on railway verification. I started as a junior research assistant on this project SafeGap, which tried to develop new verification techniques for railway verification. And then I continued in the same team working on the verification of these novel heterogeneous railway signaling systems in collaboration with Siemens as part of the industrial case study. And more recently, I joined a different team, but still work on the cyber physical systems. I try to apply new methods, for example, reachability analysis, and try to combine with the proof-based methods. But also I'm interested in autonomous system verification and safe AI. So today's topic is cyber physical systems, and the natural question is, what are cyber physical systems? I guess as the name suggests, there's a cyber aspect and a physical aspect, and there are quite a few definitions, but I guess the most popular one are systems such that there is a computer-based systems which try to control the physical processes of physical systems. And the second aspect of the cyber physical systems, there is some sort of network or communication. So one could imagine there is a network of computers trying to control a physical system. And we can find many examples in many industries of cyber physical systems. I just included a couple of pictures from potentially medical domain, where there has been quite a lot of interest in trying to integrate different medical devices in a single system, which exchange, for example, monitor the patient and provide that information to a doctor and perform some operations. Or in the airspace domain, avionics, where we have these air traffic control systems, which try to inform, or maybe in the future even control the airplanes by combining communication and on-ground navigation. One of the most important aspects of cyber physical systems, which I'm interested in the most, is that they are safety critical systems. So if they fail, there's most likely there'll be some casualties, or there'll be lots of money, which will be a cause of that. So the natural question is, how do you ensure that they are safe to operate and we can depend on them? And my research area is to use formal verification and formal methods for trying to ensure them. One particular application I'm interested, as you might have seen from the first couple of slides, is railway domain. And I guess one could reason that railway signaling systems for decades have been cyber physical systems, as for decades we had some form of computation. Okay, maybe before it was analogous computers or based on relays, and we had signalers who were back in the day were just humans, which were just moving levers and trying to change the signals for the trains. But I guess by actual cyber-physical definition, we more mean these modern-based railway signaling systems, which really use the wireless communication, use powerful computers, onboard computers on the trains to control the whole system. A couple of most popular cyber-physical railway signaling systems are European train control system, which is was initiated by European Union and now is being deployed in many European countries. And there are some versions of the same system being deployed in China and other countries. And there are different levels of the system, and starting from level 0 and ending at level 3. And this European train control system is even part of larger European railway train management system. So signaling is just one part of it. And there are some also similar systems which are used more on the metros. So one, for example, is the communication-based train control system. But all these systems have quite a lot in common. They roughly have 3 main subsystems. So they have trains. They have what's called communication centers. For example, in the European train control system, it's called radio block center, but we can maybe try to generalize as just some communication center. And we also have interlocking boxes. So just very briefly, interlocking boxes historically were in charge of allowing trains to enter special sections. So back in the day, a railway was split into blocks, and one train could occupy a block, and you would, at each block, you would have a signal. And then you would have an interlocking box, which would specify when a train can enter a block. And it would also be responsible for moving these switches, which allow trains to switch tracks as well. And in these modern railway signaling systems, we also now have these communication centers, which observe the trains and the interlocking and all infrastructure, and send wirelessly to the driver or to the onboard train system, and allowed traveling distance, or what they call it, the movement authority. So, for example, I try to sketch a just very simple scenario where, for example, this green indicates how far a train T3 is allowed to move. And in these most advanced level 3 systems, the goal is to allow trains to move almost until the back of other train, which would allow to increase the capacity of railway networks. While now we have these kind of blocks, so we lose capacity and kind of we have reduced railway performance. But of course, there are many challenges arising from this. How do you ensure that train stops in time? How do you ensure that the communication, how do you ensure that the movement authorities send the trains is safe and correct? So there's these many challenges, and the system has grown in complexity. And as said, one of the things I was interested in my PhD was this new types of railway signaling systems, cyber-physical systems. And most recent example has been this cross-rail railway network in London. And the complexity in these systems arises that you have different types of systems. So, for example, you have this European train control system interfacing, let's say, UK's national railway signaling system. And what happens, for example, in the cross-rail network, but there are trains which, let's say, start in Maidenhead in one signaling system and enter a central London, which operates in completely different signaling system. And this transition pretty much should happen on the fly. So there should be train stopping and switching computers or anything like that. The train switch on the fly. So there's quite a lot of challenges how to develop this interfaces, and I think one of the kind of more challenging bits and delays caused for the cross-rail was really how to make that interface safe and dependable. Even different types of networks, which also have this heterogeneity, for example, Thames link signaling systems, where on the same network, just based on different chain, you are running a different signaling system. So this allows to still use all their systems and all the trains, while still introducing new trains into the system. So one of the examples for this is a Thameslink system in London, where you have basically two systems overlapping, and depending which trains is running on this specific part, different signaling system controls that train. So another problem which arises from this cyber-physical nature of railway signaling systems is their hybrid nature. So trains are physical systems. They are based on physics laws, and they're controlled by onboard computers. And this European European rail train control system, the main computer which is on board is called European Vital Computer, which computes the braking curves and makes sure that the train or the driver, or if there's a driver, it obeys these braking curves. And if the driver speeds up and doesn't obey, there's a system which intervenes and slows down the train. But there is a safety critical component on the trains which tries to enforce safe behavior. And kind of key safety issues how we design these computers on board, which prevent collisions with other trains. And so how do we ensure safety of railway signaling systems, and I guess more generally cyber-physical systems? And for the next couple of slides, I'd just like to focus what has been done in the railway domain. And how I see it, formal methods have been quite successfully used in the railway domain. For example, there are quite a few examples in France, where a B method, for example, has been used to develop software for Paris Metro and airport shuttle. And quite a lot of time has been saved by doing this model-based development. And instead of this kind of integration testing, only some global tests were done on these systems. I think another application where formal methods really were fruitfully applied was verification of these control tables. So as I mentioned, in the railway, we have these interlocking boxes which define when a specific route can be enabled or allowed for a train to enter. And this is written in these control tables, and you need to make sure that they are logically sound and safe. And one of the kind of key applications of model-based verification has been exactly the verification of these control tables. There have been some novel methods developed to improve the performance of model checking based developments just for the applications of control table verification. And another quite fruitful area, and I guess a bit more recent, was the interlocking software verification. So it is exactly the implementation of control tables into our software. And quite recently, for example, some companies like Formal Route have been using automated failure improvers to prove railway software from these interlocking boxes. So, and these are kind of the formal verification areas where formal methods really did quite well. But I think for the cyber-physical systems or cyber-physical nature of the railway systems have been not really addressed. And this is where we're interested in developing a new methods and frameworks. And what we kind of try to develop is a formal development method of cyber-physical systems, where at the core is a state-based modeling language. And it could be a number of languages, and I'll talk why we selected Event-B, but it could be anything. And in particular, we're interested in using abstraction and refinement. So we want to start a fairly abstract model of a railway system or a cyber-physical system, and then through stepwise refinement, add more detail, and eventually arrive at some sort of software code. Another feature which we want to have in our framework is we want to be multifaceted. So we all know it. Safety verification is important, but we also want to provide system validation and analysis, and sometimes an animation, because even if you have a safe model, you still need to validate that it does exactly what you were intended to do, and people still want to do some animations, what's actually happening in the system. So in addition to our kind of formal modeling, we still want to provide some sort of simulation of our cyber-physical system. And another thing we want to explore or provide in our framework is to be able to find constraints or parameter values. And for that, we want to use what is called the reachability analysis. And I'm going to maybe talk a bit more in the next couple of slides. And lastly, of our framework, we want to address the scalability issues of hybrid systems. So there has been quite a lot of work in this area from different communities, but verifying hybrid systems and more generally verifying cyber physical systems is still complicated. And especially when you have large systems and let's say complicated dynamical model of a physical object you're trying to control, this is where the kind of the challenges arise. And there are many different applications and different approaches. We want to provide one which tries to combine different approaches from different communities, namely proof-based and computation-based using reachability analysis. So this is roughly the framework we're trying to develop for the cyber physical systems. And I'm gonna next talk about our kind of key point, which is this development of the pivot Event-B model, which describes the cyber physical systems. So I've already mentioned this B method, which is a formal language developed by Jean-Ramon Abrial decades ago, and it was developed specifically for the software development. But then people realized that you want to not only model the software or prove properties on software, but you want to reason about the systems. So there has been an extension, what is called the now Event-B method. And it's really the evolution of the B method, but for system modeling and verification. So what are the key features of these methods? So firstly, it's set theoretic. So the expressions you use are based on ZF theory, SF theory. And kind of the key feature is this refinement-based development. As I mentioned, you start using Event-B, the very abstract model of your system, and then through refinement steps, you add more detail about your model. You, for example, specify the data types, add new events, etc. And the idea is that eventually you arrive at a level where you could generate code. Another key feature is that it's proof-driven. So as you develop your model, in a tool, you are generated a number of proof obligations or verification conditions you need to discharge. And for that, either you can use interactive proof tactics or existing solvers or automated theorem provers. I'm going to talk a bit more in the next couple of slides. And maybe a very nice feature of Event-B that it has a very good active community, and there's quite a few tools which support development. So the main one is the Rodin platform, where you can model in the Event-B language. But also there are quite a number of other tools, for example, Beam, Model Checker, SMT solvers, or and even a theory plugin which allows to extend the Event-B language. And Rodin itself is based on Eclipse platform, so it allows to add and develop new tools for the Rodin platform and integrate quite easily. And I guess one of the more important points is that both of these methods are used quite widely in academia, but also in the industry. So for example, Siemens Transportation, Alstom, and namely other companies like ClearSea, used for real projects and mostly in railway domain. Okay, so I'm gonna give you just a brief rundown of Event-B method and what it is and how do you model it in it. And in Event-B model, you have two key components. So one of them is a context. So for example, all the static information about the model would be put in the Event-B context. So let's imagine that you want to model some cars, and you can define in this Event-B model a set of cars or set representing a number of cars. And then you can introduce some constants like this M, and then add axioms on this cars set. So for example, we want to have a set which is finite, and we maybe want to just have a specific number of cars in that set. Another kind of important part of this model is the machine. And machine what really specifies what dynamic parts of a system, so really defines the executions and all the processes. And we can, in the machine, we can have variables, we can have invariants, and we can have events which are guarded and have actions. So for example, in here, I'm just having a small example of a machine which increments a variable x starting from 0. So all machines have to have an initialization event. So for example, we have x, which is just initially set to 0. And then we have a just single event increment, which will add a +1 to the x variable. And what happens then is that you are provided with a number of different proof obligations. So for example, I introduced a simple invariant, which I want to prove in my system. And basically, I just want to make sure that my model, my x, never goes above 12, I guess, yeah, above 12. So what happens is for each event in the model, there is a proof obligation generated, which asks to prove that this basically holds. And this is what's called invariant preservation. But there are also other types of proof obligations you need to prove, for example, that well-definedness rules, or feasibility, or refinement, strengthening, etc. And on kind of purely discrete level, there has been quite a lot of work, and there has been different tools integrated in the Rodin platform. So it achieves quite high automation and verification of discrete models. But we'll talk where the problems occur when you have a hybrid system. So just to show what maybe happens when we want to prove a rule. So for example, we have this one type of proof of obligation, invariant preservation rule. And what tool asks us to really prove is that after we apply action 1 in event increment, that invariance 2 still holds. And because I added basically a guard, which makes sure of that, this could be quite easily discharged. But what sequence we get? Basically, we get some axioms in previous invariants. So for example, invariant 1 would be here as well. And then what you would need to prove in a sequence is that action 1 is still ensures that invariant 2 is preserved. So basically in this model, you get 2 proof obligations for initialization event, because that still modifies your x variable, and for the increment event. And just another type of proof obligation conditioning to prove is called feasibility. So as you can see here, there is other way to write in Event-B actions. So previously was a direct assignment, but there is a way to write in a form that says basically change x such that the next value holds like this. So there is a way to add an assignment such that, which kind of allows you to automatically prove, let's say, your invariant 2, because you can add that predicate in your such that assignment. But then basically Event-B and Rodin platform asks you to prove a feasibility of such event. So basically you need to prove that exists such X prime that this holds. So there is a way to rewrite your actions that you can basically discharge some, let's say, invariants, but then you need to prove feasibility of such a events based or actions. And why this will be important, we'll see how Event-B can be used for the hybrid systems. So what we want to achieve basically with Event-B, we want to move from discrete Event-B to allow modeling cyber-physical systems. And as I said, one of the kind of key aspects of cyber-physical systems is this physical aspect, which basically is mostly about the continuous aspects of the system. So for example, systems which can be defined by differential equations. So one of the key developments in this Event-B community has been development of Rodin theory plugin, which allows to extend Event-B mathematical language. So for example, with this plugin, we can introduce new operators such as like sequence, which hasn't previously been as part of the Event-B language. And it allows you to create new types, new operators, which, for example, help to define sequence, where then we can use direct definition of what sequence is. It also allows to add axioms about what a sequence is, and also allows to include proof rules. So when we eventually reason about sequences in our model, and there's maybe proof rules which allow you to discharge your sequence much more efficiently. So with this introduction, there has been two main directions of work which enabled Event-B to handle continuous systems or hybrid systems. And maybe just to quickly define, the hybrid system as a system which combines both discrete and continuous behaviors. And quite typically, a hybrid system is modeled to use a hybrid automaton. So one of the works has been done by Richard Barnach and his colleagues. And it was done basically by extending Event-B language without using a theory plugin, by introducing new types of events called appliance events, which really just models continuous systems. Unfortunately, this approach is not tool supported. So maybe it is less practical and just doing something more realistic. The other approach is by Dupont in his PhD work. He really used the theory plugin to develop new theories. For example, starting from reals, continuous functions, building up to differential equations. So building a large library of theories in Event-B, and then adding different types of modeling patterns and refinement patterns, which allow you to specify hybrid systems in what is called a hybridized Event-B. And so to build our framework, we decided to use the latter work. It's a bit more practical, and you will see how we use it. And what this work depends really is on two key concepts. So as I said, there's new sets of theories which allow you, for example, to define differential equations. And in his work, he introduced a number of useful operators which you need to reason about hybrid systems. So for example, sometimes you need to check if a function is a solution of differential equation, or whether even that differential equation is even solvable. He also added a number of useful axioms when you try to reason about these systems, for example, about continuity of some of functions, which is a Cauchy-Lipschitz axiom. And one of the key operators which he used to extend this language was this continuous before-after predicate. And as you can see, it really relates to this such that operator. And we basically now have a situation where we want to actuate a continuous function. So we want to make a step, or we want to extend its evolution. And we need this continuous operator to do that. And this operator has really three parts, which are necessary to ensure when you're trying to make adjustment to a continuous function. So one is you need to make sure that the next step satisfies the past. So you can have a step which is disjunct from your past. And here, if you have, for example, some continuous variable, xp, which is a function from time to some continuous state space, we want to make sure that the next evolution is connected to the previous evolution. This is a domain, if I remember, domain restriction. So we want to make sure that the past is connected to the next evolution of the continuous variable. Then we want to make sure that the next step of or next evolution of the continuous variable satisfies some generic predicate. So again, we want to have some sort of form of predicate which connects the next evolution and the current XP value. And lastly, we have some predicate on the evolution domain. So we want to make sure that our continuous variable evolves within predefined evolution domain of this differential equation, for example. And for that, there is like, for this whole operator, there is a shorthand, which I'm going to maybe use a little bit. And next part of this whole framework was the generic events. So in his thesis, he wanted to provide a generic hybrid system model. And for that, he used a kind of generic hybrid system closed loop system, where you have, in reality, 4 types of events. So you have a sense event, which senses the environment and then makes adjustment to your controller. You have actuation event, which actually makes continuous functions or this physical process to evolve. You can also have some effects from environment, which also affect the continuous behavior of your system. And you also can have direct commands from, let's say, controllers. So for example, a train driver can make a direct command to the controller of the train, for example. So in this work, he defined a generic hybrid system model, which has discrete events, for example, specified by modes of a hybrid automata. Let's say it could be move freely and restricted, where you try to stop it. And then you have a continuous variable, which maps from time to some S variable, where S would be typically some vector space. And lastly, you want to make sure that that the domain of this continuous variable matches the time in the model. And just very briefly, I'll show you how we model these 2 types of events. So one is the actuation event, which propagates the evolution of this continuous function or differential equation. And the other one is discrete event, which really just models how the controller mode is changed when the changes in the environment or physical state has been changed. So here we have a actuate event. We have a number of parameters, and then we have a list of guards, which make sure that the next iteration or next evolution of time is incrementing, so we cannot go backwards and time has to move forwards. Then we have some sort of predicate on our evolution of system. So maybe this is some sort of safety invariant on the evolution, for example. And then we want to make sure that a solution of this differential equation is actually feasible. So in this level, we can add a guard which would allow us to discharge this proof obligation without actually solving a differential equation. And sometimes we want to be in specific state of the controller, for example, in specific mode of hybrid automata. And lastly, we can have a guard which specifies the evolution of continuous variable, this evolution domain. And what happens really, we have an action in this actuation event, which will evolve the continuous variable from time t, the current time, to some time in the future, and that XP has to satisfy, or the next XP has to satisfy some predicate, which in the future refinements will be specified explicitly, and this evolution has to satisfy this evolution domain of the differential equation. So this one type of event, and there is a very similar event called behave, which models the effects of environment rather than the physical action. And very similar, that we have a sense event where we have some controller, for example, where it is in some state S, and it has some physical state, as you can see, power set here. And the only thing we want to change is switch from one state to another. And this operator basically says to switch to any state within S. So without, it's kind of non-deterministic choice here. And just the last part on this framework is, because you introduce new types of operators and theories, you get new types of proof obligations as well. So we briefly talked about this invariant preservation rule, but now you have this continuous invariant preservation rule where you need to prove that the evolution of the continuous function satisfies your invariant at all times. So it's kind of a way of doing inductive proof where you prove that initially you're in safe state, and then you need to prove that every actuation event also satisfies that safety invariant. Other type of proof obligation you can get is this continuous feasibility, where you need to prove that actually the solution to a differential equation is actually possible. So, and kind of importantly, these types of proof obligations are generally, even in hybrid Event-B, but in other kind of frameworks, very hard to prove, and you need to use some sort of interactive prover, and basically it's very hard to be done, especially for more complex systems. And how we want to integrate this is really to use the theories and the generic model as the starting base for developing any cyber-physical system or any hybrid system, where a user would try to instantiate this generic model and these generic events and develop domain theories. So, for example, railway theories and railway events from the starting point of this generic model. So, in principle, we just really want to use these patterns as a starting block, and then use a refinement provided by Event-B to add more detail about specific system we're trying to model and try to prove some properties. And I'm going to show just one example how we used this hybridized Event-B to develop a railway signaling system. And as a first refinement of this generic model, we wanted to model a speed control of the railway system, of the train. And we can know that what driver or automatic train operation system can really do is not directly control acceleration, but rather controls the power or the tractive force which goes into the engine, and from there it yields acceleration. And this is typically modeled by what's called the Davis resistance equation. So it's a nonlinear second order nonlinear differential equation, which we use to model kind of a rolling stock behavior. And from there, we just described a simple speed controller model with two modes, a free mode and restricted mode, where in the free mode, the train can accelerate as much as it wants until it reaches the end of movement authority. So there is a variable called end of movement authority where a train has to stop. And we have another function called stopping distance, which computes a stopping distance of the train given the current speed and the acceleration of the train. And then if the train is in restricted mode, it applies some brakes and tries to come back to the free mode again. And for that, we instantiated or developed a new theory in trains. So what we really did was use this Davis equation and defined a new theory in trains, which then could be used for modeling any railway system. So it's reusable. And this train theory really contains just a formal definition of this Davis resistance formula and adds other axioms about it. And what's the next step was to define the static information context in Event-B, where any other parameters of this train model would be used. So for example, Davis equation has these coefficients, which affect well, they correspond to some drag forces in the from air or from the rail itself, and we specify them as some sort of constants in here. And then also we defined the stopping distance function, and also these two modes we model our hybrid controller. But the main part was this modeling of the this dynamic part, and we define a machine which introduces the continuous variables for the position, speed, and acceleration as the functions from time to a real. Again, we have similar invariance as in the generic model. And we also introduced a additional variable for modeling this end of movement authority, which defines this the kind of the point or the distance where the train has to stop. We also introduced this variable for traction effort, F. And importantly, we specified two main properties we would like to prove in this model. So the main safety property is that we basically want to make sure that the speed controller always ensures that the train is within end of your movement authority. So it never goes out and leaves that allowed authority. But also we can prove properties about the physical parts or physics, where basically we must ensure that the speed here is never below zero, because that's physically impossible. And just a couple examples how this really looks in the model. So for example, we have sense to restricted event, which refines our generic sense event from the patterns I described before, which really tries to model a situation where a sensor senses that the limit of the position to the end of authority is reached, and now we need to enter this restricted mode. So we have just a single guard which looks at the position of the train and also the stopping distance, and then just make sure that if this is true, we enter restricted mode. And just the second type of event, we have the actuation event, which models the changes in our continuous variables, so acceleration, speed, and position. And we use this kind of predicate from the theory of Guillaume's, which says basically that the solution of these is a solution of this Davis equation, which models the train itself. And here we have this evolution predicate, which makes sure that we don't go out of this end of movement authority, and we basically ensure that the speed doesn't go below zero. So we use this trick where we enforce our invariant in the actuation event, but then we need to prove that this is actually feasible. And just to show how many these types of proof obligations we get in this refinement is in total 55. And we have 18 invariant or discontinuous invariant preservation proof of conditions. And well, close to most of the, 8 of 18 have to be interactively proved elsewhere, because it's really complicated to do it in a hybridized Event-B at the moment. And same for these feasibility types events, that basically all of them have to be proved elsewhere, or they cannot be proved at this level. So in this work, we tried to kind of see if we could use alternative techniques to help our proof effort. And one particular technique we've been looking is the reachability analysis. And it's a method for computing all reachable states of the system. So as you can imagine, let's say we have some initial set of positions of a train, and then using reachability analysis of dynamical systems, we can compute a set of all reachable states, which started in this initial set for time t. And if you combine multiple reach sets, you have what's called a reachable flow pipe. Reachability analysis also can be used for a hybrid automaton, but it's a bit more complicated than that. So we wanted to investigate whether reachability analysis can be used with proving some of the proof obligations about feasibility or discontinuous invariant preservation. Similarly, how model checkers have been used to do that for discrete systems. And as a first attempt, we decided to use a tactic. So the verification tactic of this is as follows, where we really try to first strengthen our evolution domain of this continuous variable, such that it is stronger than invariant we're trying to prove. And as we've seen, if we do that, we basically, what we get, we discharge the continuous invariant proof obligations, but then we need to prove that that these types of events are feasible. So we get basically proof obligations for continuous feasibility. But what we can do with that is that we can translate these feasibility events into a reachability problem. And for that, we used a reachability tool called Julia Reach. And for now, we had to translate manually. And we also have to translate other parts of the model. So for example, stopping distance function had to be translated as well. And we also have to translate the dynamics of the model and other parts of the system as well. And then, unlike what you do in a proof, in this reachability problem, you need to define your initial set. So you move from the symbolic proof-based verification to really some sort of computation using predefined intervals. But it allows us to really compute this reachable set and then to check whether this feasible region, which is permitted within our evolution domain, is basically exists. And what we're really trying to find is we're trying to find this interval on time from 0 to some t prime, for which this evolution satisfies our predicate for this evolution domain. And how this affects our proof statistics, it allows us to basically discharge invariant preservations automatically by strengthening the actions and the predicates. But then we have these feasibility proof obligations, but these can be now exported to the reachability tool and approved remotely. So we sacrifice this invariant preservation for this feasibility. We also, as part of the framework, we said we want to allow animation and simulation. So another thing we did, which allows us sometimes to fine tune or validate our models, is we tried to connect to the Simulink. And so we also implemented this hybrid speed controller model in Simulink, and we used the French trains TGV with their Davis coefficients to just validate that what we models actually make sense in the sound. And then what our approach allows to do is to distinguish two problems. So in the first refinement, we basically tried to prove that the speed controller, which is used on the trains, and if it's given this end of movement authority distance or position, can make sure that it stays within this position. But then another natural question is, how do we know that this distance or the point where the train has to stop is issued and is safe? And this is another level of problem. And so the next refinement was to introduce other subsystems of the railway signaling system, as we described the interlocking and communication centers, and also model this protocol. So what we tried to create a generic railway signaling system, which is really based on ETCS level 3 and the CBTC system. And we used previously developed Event-B communication modeling patterns to describe this generic communication protocol. But the nice idea is that this model then could be even further refined to actually model ETCS level 3 and CBTC. And the main safety kind of verification objective was to prove that when this end of authority or moving distance is issued is actually safe. And also when the train moves over these railway switches, which control where the train can move, is actually fixed. So what sometimes can happen when this switch on the railway is not fixed and the train can derail. So there is another safety property to do here. So the second kind of refinement was much more automated because it didn't have any kind of hybrid aspects anymore. So it could be discharged much easily. And after 2 refinements in this kind of our final model of a system, we in total had 140 proof obligations, and majority of them, 119, were approved automatically, and only 21 had to be used, had to use interactive prover. Okay, so just in summary, that we think we propose this development framework for cyber-physical systems, which believe refinement and abstraction can help to address the complexity of this development. In particular, we feel like this distinguishing the problems where, for example, in one refinement, we can prove a safety of controller and then prove the safety of the whole system allows us to kind of simplify the problem. We're also very interested in further exploring this reachability analysis and its help for automating the proofs. And we believe for the next step, we really like to kind of develop a more automated translation between the hybridized Event-B models to a reachability tool, Julia Reach. And also, we realized that some new Event-B theories are needed. Because, for example, in a reachability community, we quite often use matrices to represent dynamical systems, and this currently is not available in Event-B. But maybe just to make a bit more long-term future work, I think there are more synergies between proof-based and reachability-based cyber-physical system verification. And I think we just really made some very first steps where we tried to prove a single proof obligations, and we still have quite a few open questions to address. But I think in the future, we think like there could be a more kind of interaction between them. For example, one of the areas we would like to look into perhaps is when you have a large hybridized Event-B models, maybe a whole submodel could be proved and using reachability analysis instead of single events or using or just a single proof obligations. Also, reachability allows you to kind of find the constraints and parameters of the values of the model. So instead of like doing the forward reachability analysis, you can do also a backward reachability analysis, which provides you the safe initial state space rather than using as kind of a verification approach. And the last bit, which we really interested in, is the ability to move from the continuous model, which we kind of now support, to a discretized and maybe eventually to code generation. And we think maybe using reachability analysis, we could help to discover these T primes, which would be the sampling rates of a system, for example, or discretization steps. And so really just like to thank my colleagues from a number of universities, which this is clearly joint work. And I have a number of colleagues who help to contribute towards the Event-B development and help me to understand the railway better. And if I have just a second to plug, we are organizing a small workshop on the cyber-physical systems in Bristol, which is quite local here. So please consider coming just to networking or even submitting a short paper. And we have great invited talks from Anna from York University and Claudia from Aarhus University. And just have lastly a couple of references, which I'm happy to share. But yeah, this is kind of the end of my talk.
Thank you very much, Paulius. It was a very interesting talk. If anyone has any questions, please unmute yourself and ask.
Hi, Paulius. Thank you for a very interesting talk. I had one question regarding your attempts at automatically discharging invariants. Have you considered either other deductive methods of constructing continuous invariants or combinations of other invariant synthesis methods with reachability analysis, as I know a fair amount of work has been done in this area, connected to, say, differential dynamic logic?
Yep, so I know Guillaume tried to compare differential dynamic logic with his approach. And maybe just quickly, there's a set of different work for modeling hybrid systems. And done by Andre Platzer, and it tries to use hybrid programs and dynamic logic to reason about them. From what we kind of see, that the main problem is that to prove them, you need to manually come up with this differential invariant, which is kind of is a bit tricky for more complex systems. And I think only very recently they introduce some form of refinement. So we believe of the refinement, you can kind of handle larger cyber-physical systems compared to their more hybrid system, smaller models. But I think, just there is kind of issue of this trying to come up with this differential invariant, which is tricky. But they have been doing some great work in trying to automate that as well. I should point out.
Thank you. I've seen a thesis from Andrew Sogokon who was at Edinburgh for his PhD, looking at synthesizing differential invariants, which might be relevant to, I'm not sure how that compares to the automated methods you were looking at using reachability analysis, but I think some of his methods also used reachability analysis in a different way to tackle liveness. Right.
Yep.
If that's interesting, I can share it, as it would be interesting to see how techniques transfer from the two contexts.
Yeah, I'll be grateful. Yep, please.
Any other questions? Okay, I had one. It's about the reachability analysis tools that are available. Do they support differential equations on manifolds or differential algebraic equations?
Would you say again? Do they support differential equations
on smooth manifolds, or I guess differential algebraic equations? Kind of when you have the equation, but you're looking at for example, the surface of a sphere instead of looking at R3.
Yeah, I don't know about the. Yeah, I don't know. I will need to check on that. Yeah.
Because I know of one tool. It's not exactly for integration, but for optimization on manifolds. There's one version. It's called ManOpt, and there's one version for Julia. But I don't know if it would be helpful for reachability analysis in any way. But it would be interesting. It seems like, because we've been working at York with trying to come up with hybrid models of robots, and as soon as you start getting more interesting robots, you start the equations are no longer well behaved or simple. So yeah, I think there are different approaches to deal with this extra restrictions on the equations, but I don't know if the available tools have any support for that kind of model yet.
But just to understand, so when you move more complex models, you said you need these differential manifolds to capture the system?
I don't think you necessarily need, as far as I understand, there are ways of converting these equations into ordinary differential equations in some cases at least. But what you get from the theory, I think in a first instance, might be something that's not just a differential equation. It would be a differential equation with an extra constraint over the possible domains and solutions.
Yeah, I don't think I've seen anything apart from just normal ODEs or hybrid systems, but I could have a look. Yeah, that's
Thank you.
interesting.
And since I mentioned these models for robotics, do you have an intuition of how much more difficult it would be to deal with more, perhaps less restricted hybrid models than what you would get on a model of a train? I mean, I'm assuming that there will be a little bit more less structured, perhaps, than traditional models. Do you have an intuition of how much more difficult it would be to deal with those kinds of models using your methodology?
But do you mean like when there is more uncertainty in a way, or the let's say you don't have this hybrid automaton of robot, or in what sense?
So one example that I'm thinking of is, I don't know if you've ever seen this robot. It's almost like a mechanical arm, but it has some purpose to keep things vertical, for example. And it has, I don't know, 4 different arms all connected to the same platform. So it ends up with loads of joints and links. And if you try to calculate the equations of motion of the whole thing, if you don't simplify it, it's a massive set of equations. And I don't know how current techniques would scale for these more, I don't know if complex, but at least more complicated equations, if we don't linearize them or simplify them in some way.
Yeah. So kind of our approach was really to export that complexity to reachability analysis, because otherwise it's really unfeasible to do proofs on, I would imagine, even more systems. From what I've read and seen, reachability can handle fairly complex systems. I've seen 16-dimensional F-16 models of the jet fighter, maybe even more complicated. Yeah, so there's I guess complexity aspect from the dynamics point of view, which we can handle in the proof, so we export it. We are better maybe at handling the complexity of hybrid automaton, so we can add more states, and that's not that much of an issue as long as kind of the dynamics are easier. But I guess in your case, it's kind of both, where you have a very complex dynamics and probably non-trivial hybrid automata of a robot itself. Yeah. So
Thank you.
I would say it's still quite a long way, I guess, to go to really complex. Yeah.
Thank you. Does anybody have any other questions or comments? Arjun, go ahead.
Hi, can you hear me?
Yep.
Yep.
Yeah. There was something earlier on, so I wasn't quite sure though, when you're introducing Event-B, you were talking about at some point an axiom for Lyapunov stability. I was wondering if that was something which is sort of integrated into the system, or is something that the user could define, so the user could define other types of stability, for example.
So the theory itself is extendable, so you can extend the theory yourself. I think the theory was about continuity. I think maybe Cauchy-Lipschitz, but I've seen works from what actually Thomas mentioned, which used this differential dynamic logic for proving stability. But yeah, we don't have much axioms or for the proving stability, but they could be added quite easily. Yeah, as long as you know the axioms.
Thank you.